Hi, my name is Josh Benabou, and I'd like to tell you about our paper, Search for Axions in Magnetic White Dwarf Polarization at Lick and Keck Observatories. This is work with my collaborator at UC Berkeley, Benjamin Safdi, at the Flatiron Institute, Chris Desert, as well as a great team of astronomers at Berkeley, Kishore Patra, WeiKang Zheng, Thomas Brink, and Alex Filippenko. Axion-like particles are strongly motivated hypothetical particles, which naturally emerge in string theory constructions. In our work, we performed the most sensitive search to date for axion-like particles of low mass, less than 2 × 10⁻⁷ electron volts. We do so by collecting spectropolarimetry data with the Keck and Lick observatories towards magnetic white dwarf stars. The physical effect which allows us to search for axions in this data is that the magnetic white dwarf stars emit optical photons from their surface. These photons may convert into axions in the strong magnetic field of the star, which takes typical values on the order of hundreds of megagauss. In order for these photons to convert into axions, they must have a polarization which is parallel to the local direction of the magnetic field. And this means that completely unpolarized light leaving the surface of the star would then acquire some level of linear polarization in the presence of conversion into axions. The non-observation of this linear polarization allows us to place constraints on the axion-photon coupling Ga gamma gamma. In order to compute the level of linear polarization induced by axions, we need to know the magnetic field of the star. For the stars observed in this work, we constrain the magnetic field geometry through Zeeman intensity modeling, meaning that we use the magnetic field dependence of the locations in wavelength space of the Balmer alpha lines of hydrogen. We are thereby able to constrain the magnetic field on the surface of the star by measurements of the flux as a function of wavelength. In order to constrain the magnetic field geometry, we need a model of the magnetic field, and we begin with a simple model of a dipole offset by some amount along the direction of inclination of the star. And we are able to construct posterior distributions of the quantities parametrizing this model using standard Bayesian methods. We also examine a more complicated model, a spherical harmonic expansion up to the second harmonic. Once the magnetic field geometry is constrained, we compute the level of linear polarization induced by axions by solving the classical equations of motion of the axion mixing with the photon as waves propagating from some surface element of the star to the observer. We then model the polarization, and in particular the reduced Stokes parameters U and Q, as the sum of this linear polarization from axions, as well as some intrinsic astrophysical polarization and an eventual instrumental systematic offset. We characterize the instrumental systematic uncertainty by measurements on standard unpolarized stars. We then draw at random samples from the posterior distribution of the magnetic field geometry, and for each compute a joint likelihood over U and Q to derive an upper limit at 95% confidence on the axion-photon coupling J gamma gamma. This generates an ensemble of limits, and as our fiducial limit, we choose the weakest one at 1 sigma. We also generate an ensemble of discovery test statistics of the astrophysical component of our measured polarization. We perform this analysis towards for 5 observations towards 5 magnetic white dwarfs. In summary, magnetic white dwarfs emit optical photons, which may convert into axions in the strong magnetic field around the star. This induces a wavelength-independent linear polarization in the observed starlight. By analyzing the Stokes parameter data, which we collected with the Lick and Keck observatories towards several magnetic white dwarf stars, we find no evidence for axion-induced linear polarization, and we constrain the axion-photon coupling to be less than 1.7 × 10⁻12 inverse GeV for masses, axion masses below 2 × 10⁻7 eV. Our results disfavor the proposed axion explanation for the so-called gamma ray transparency anomaly, and also strongly exclude the axion interpretation of the non-attenuation of high-energy gamma rays from the gamma ray burst 221009A. Thank you for listening, and we hope that you'll check out the paper.